Hello everyone, my name is Saim and I'm a student at IIT Indore and I'm working on a project design and analysis of wideband hygiene and uh, reflector wideband hygiene reflector antenna for beam steering application. So here I'm presenting my work uh, along which we have published in this conference and so these are the outlines of my presentation. So all these things I'll be covering in the upcoming slides. So reflector antenna consists of a feed along with the array of elements that are arranged along with the elements and the patches that are arranged in such a way that when a wave is incident on it, it gets reflected in the intended direction. So this make us to control the reflection of a beam. We are steering the beam in the intended direction. So phase controlling, we can control the phase of the incoming wave by varying the geometry of our patches that we are using in our array. So as you can see that here in this figure, I have shown phase tuning that being achieved in a design, and then we are tilting the beam at an intended angle. So this is something what Reflectarray does. So we have currently parabolic reflector, and how our Reflectarray is better than this. So parabolic different dish and reflector are conical type reflectors. So they just concentrate the beam at their focus. When they strike on when panel beams strike on the surface, they get concentrated at the focus. So they are very much bulky. They are very much large and very much heavy as well. And they obviously whatever the beam in the surface, it will get band to their focus only. So we generally don't have the beam electronically beam steering in this case. But Reflectarray, on the other hand, is very much light in weight. It's a planar surface, which provides us to make the beam electronically controlled. So when it comes to Reflectarray, so phase tuning is one of the most important step while designing the Reflectarray. So one should opt the right method depending upon depending upon his or her design. So we explore various methods, and they are time delay, variation of time delay line, and then we have patch size variation, and then we have angular rotation of patches. So by doing all with these methods, we can get the different we can achieve the phase tuning in our Reflectarray, and we can control the beam. So depending upon my design, I opt for second option, which is the variation of sizes of patches. So one of the biggest limitation that people come across in while designing the Reflectarray antenna is its limited bandwidth. So bandwidth is one of the major issue, and we try to tackle this limitation in our research, along with various limitations like light in weight. It should be light in weight, and it should be a bit more compact, and size should be as small as possible. So in order to incorporate in sensing applications, which is the theme of this conference. So we have various methods to get the wider bandwidth, and these methods are multi-layer structured puninsel and reconfigurable Reflectarray. So yeah, so also we have explored these three methods, but one should opt depending upon his or her design. Like in my design, I was trying to make a beam, my structure light in weight, small, light in weight. It should be compact. So multi-layer was not that good option for me, and reconfigurable at the same time making it more complex. So puninsel was the option that left with me, which has multi-resonant element. We get multi-resonant frequency, which provide a better bandwidth, better phase tuning, and hence better bandwidth. So reconfigurable is something I'm working currently. So puninsel I have done and published it, and now I'm working on reconfigurable, making it reconfigurable. So you can see here we have the puninsel cycle, which I have took from this paper. for your reference. And you can see like how these patches are varying the dimension, and we are varying the inner loop. By varying the inner loop, this person is getting the phase tuning and reflection, which is more than 90%. So yeah, this is how the Phoenix cell works. So this cycle repeats itself. So we are bound to only these many cycles. So yeah, unit cell design. This is the design of my unit cell. Like I have, my research objective was to design Reflectarray, which must be light in weight. It should incorporate the 3D printing technique. So, and the next step is to enhance the bandwidth as well as gain of the system. So as I told you that my objective was to make the design very compact, very small and light in weight as well. So I took an incorporation of 3D printing. So I'll use PLA, which is 3D printing material, and I keep the thickness of my substrate is 0.15 mm, which is the least possible, and air gap 1.5. And again, to strict my ground copper, I took another substrate which is 0.15 mm. So in order to make the design more lighter, I just simply in between two substrates, I didn't put any material. I just keep the air inside it. So this makes my design very much flexible at the same time, and very much light in weight and thin, very thin. And here I have shown the result which I have got. Here I'm getting the phase tuning of more than 320 degree and a phase reflection of more than 93%. My 93% of the wave that are incidenting on this array has got reflected more than 90% reflection we are getting here. And this is the cycle that we are using. This patch sizes it's varying, and depending upon the size, like for 2.5 I'm getting a phase of 135. For 8.7 I'm getting a phase of 90, and 9.92 I'm getting a phase of 45. This is the same, and in the same way I'm getting these phases. So yeah, so this is the phase formula that we have used to obtain the phase profile. And like if here I need phase of 135, so I will replace it with a patch of 2.5 mm. This is how this phase profile is shown over here. So this obviously, when we use this equation to get the phase profile, that phase would be there will be infinite number of phases. So we need to quantize those phases, and we did quantize and we did quantize it to make the design practically realizable and to fabricate it. So I used 3-bit quantization, and I quantized it into 9 levels, and we have used these equations to quantize the beam, and we run the same, and we got this profile. This is the quantized version. Obviously, this is the approximate, but we are getting very good results, which are very much similar to the phase profile that we got before the quantization. So we focus on those objectives that we should steer the beam at 25 degree. Frequency at which we operate is 10 gigahertz, and the antenna position is 148, and elevation is 25. So yeah, we are bending our beam at 25. This steering is very much important for reflectarray design. Like I'm putting my antenna right over the top of my reflectarray. So if I don't provide any beam steering to my wave or my incident wave, it will go directly above the, and the trajectory will be the same that it was before the incidenting, before the incident, and this antenna will cause the blockage. So in order to avoid the blockage, we need to provide 25 degree, like you can bend it to any angle, but I bend it to 25 degrees so that it can go like in that way. It should not strike with the antenna again. So I prevent this blockage and provide this 25 degree. And whatever the angle at which we need to bend, accordingly we will be having the configuration of the arrangement of these units with different angles. For different angles, we are in different arrangement. So in this, I've shown my results which I have got. Like here you can see, like first I have shown the gain without PRA. and with blue, you can see. And with PRA, like phase reflect array, we are getting this much. So we are getting the gain enhancement of more than 10 dB, which is 10.6. And obviously we quantized our beam. So instead of getting banding correctly at 25, we are getting it at 23. And this is working in a frequency range of 10 to 11 gigahertz, which is a quite wider. So this is the result with PRA, phase reflector, and without. So we have significant gain enhancement. So comparison table, like this is the comparison table of my work with the work that done by the that has been done by other researchers. So these are the frequency and gain enhancement, and obviously like this, I'm using the 3D printing technique to making it more flexible and more light in weight. Like, and obviously it's making it more cheaper and low cost. Like PCB fabrication is more costly compared to 3D printing. So this is the fabrication. Like first I use the 3D printer to get my substrate ready, and then I transfer the impression of all my pages onto the substrate, and then I use the vinyl cutter for that to cut the square like patches of copper, and then I transfer it manually on this reflector, which was very much like difficult to do that. But to overcome all this limitation, like copper patches, so many copper patches were getting waste while transferring it to manually to reflector. So I use this silver ink. Like we explored various methods, and we come to another silver ink can also be used to in order to avoid this usage of vinyl cutter and then manually transferring. Like we can just simply use silver ink for that. And obviously silver ink is can eliminate the use of vinyl cutter, and we don't use any machinery in that case. Yes, sir. We can only 3D printing is used to fabricate this structure. We don't need any other machinery, and here also we are getting a gain of more than 10 dB. So these are the conclusions. So we have developed our reflectarray antenna, and we tackle the limitation of narrow bandwidth, low gain, and thick profile. So we have made wideband reflectarray with high gain and thick, very light profile. Like here I have shown like bandwidth has got increased. Like for 1 dB we are getting 14%, and for 3 dB we are getting 22.68% bandwidth. And yeah, so we have got the gain enhancement at 10.6, and we have steered the beam at 23 degrees instead of 25. By quantizing, we got it to 23 to avoid the blockage, and we make it light and weight with the use of the PLA and the air substrate. So these are the future work. Yes.